Imagine this. You're standing at the edge of the universe, staring into the void, and in that darkness, there's a flicker, a faint glimmer from the past. It's not just any glimmer, though. It's the light of a galaxy that formed just a few 100 million years after the Big Bang. That's less than 1% of the time the universe has been around. To put it in perspective, if the entire history of the universe were a 24-hour clock, this galaxy would have formed just moments ago. That's the magnitude of the discovery we're about to dive into. For centuries, we've peered into the night sky, fascinated by the distant stars and galaxies, trying to piece together the story of the universe. But for the longest time, the earliest galaxies were just a mystery, a part of the cosmic timeline that we could only imagine. Well, that's no longer the case. Thanks to the groundbreaking work of the James Webb Space Telescope, or JWST, we've been given an extraordinary window into the past, one that allows us to peer directly into the very dawn of the cosmos. In one of its latest missions, JWST has uncovered the most distant galaxy ever detected, JD's GSZ 130. This galaxy formed roughly 300 million years after the Big Bang, at a time when the universe was still in its infancy, full of chaotic energy and dense gas clouds. For perspective, the Big Bang happened about 13.8 billion years ago. So we're talking about a galaxy that was born during the cosmic dawn, a time when the universe was still evolving, shaping itself into the vast structure we now know. But why does this discovery matter so much? To understand the significance, we need to explore what exactly we're looking at when we study this galaxy. JD's GSZ 130 is not just another pinprick of light in the distance. It's a key to unlocking the mysteries of the universe's earliest days. It represents a moment when the universe was still young and malleable, just beginning to take shape. It's like discovering a fossil that hasn't just been preserved in the rock, but has been frozen in time, offering insights into an ancient world that no longer exists. This galaxy doesn't just represent the birth of stars and galaxies, it represents the birth of the very building blocks of the universe as we know it. The elements, the radiation, the gas, everything that would eventually form the complex structure of our universe was coming together in galaxies like this one. And JD's GSZ 130 gives us the rarest glimpse of that process. But there's more to it than just the beauty of observing a distant galaxy. JD's GSZ 130 has the potential to radically change everything we thought we knew about galaxy formation. Before the advent of JWST, scientists used the Hubble Space Telescope, HST, to peer deep into space and detect galaxies from about 500 to 600 million years after the Big Bang. That's impressive, but it's still far from the beginning. JWST's infrared technology, however, lets us peer back even further, into a time when the universe was much more energetic and chaotic. This new discovery shows us that galaxies like JD's GSZ 130 weren't just the first to form. They were also incredibly efficient at doing so. For years, scientists believed that galaxies took their time to coalesce, gradually gathering gas and dust over millions of years. But JD's GSZ 130 paints a different picture. This galaxy formed in just a few 100 million years, a rapid process by cosmic standards. It suggests that the universe may have been much more efficient at creating galaxies than we previously thought, opening up all sorts of new questions about how the first stars ignited and how galaxies came together so quickly in the early universe. Now, let's take a moment to appreciate just how mind-boggling this is. The universe was a very different place back then. The cosmos was still filled with a vast sea of hydrogen gas, mostly untouched, unburned. There wasn't the complex network of stars, planets, and galaxies we see today. Instead, there were dense clouds of gas and dust swirling around, gradually coming together under the pull of gravity. The formation of galaxies in those early days was a delicate, violent dance of energy, matter, and gravity, all interacting in ways that were, at that point, barely understood. But the biggest surprise: these galaxies didn't just form rapidly, they were also shining incredibly brightly. This tells us something about the processes that were going on inside them. The first stars were likely much more massive than the stars we see today, burning through their fuel much faster, and emitting enormous amounts of light and radiation. This is a key clue to understanding not just the galaxy's formation, but also the overall evolution of the early universe. So what does JD's GSZ 13.0 tell us about the universe and how it evolved? It's a key to understanding galaxy formation and the early conditions of the universe. It challenges everything we thought we knew about how galaxies come together, suggesting that the universe was much more dynamic and energetic in its youth than we ever imagined. And here's where it gets even more exciting. This discovery is just the beginning. As we continue to observe galaxies like JD's GSZ 13.0, and as JWST pushes deeper into the past, who knows what other ancient cosmic relics we'll find. The universe has so many stories to tell, and we're just beginning to unlock them. Before we dive deeper into the science of galaxy formation and what this discovery means, let's step back for a second. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. Now, with JD's GSZ 13.0 fresh in our minds, let's take a closer look at what this galaxy's rapid formation tells us about how the universe's first galaxies were created. Now that we've met JD's GSZ 13.0, the most distant galaxy ever discovered, it's time to unravel the mystery of how galaxies like this one actually formed. Imagine the universe just after the Big Bang, a chaotic, sizzling soup of gas, energy, and particles expanding at unimaginable speeds. There were no stars, no galaxies, just a vast, empty canvas waiting to be filled. Over the next several million years, that blank canvas began to take shape, slowly and with a lot of turbulence. In the beginning, the universe was incredibly hot, so hot that atoms couldn't even form. Instead, there were just particles of light, energy, and fundamental particles like protons and electrons. As the universe cooled, these particles began to coalesce into atoms, mostly hydrogen, with a small amount of helium. This was the first step toward the formation of everything we see today. But how do we go from a hot, dense cloud of gas to massive galaxies with stars, nebulae, and black holes? For centuries, scientists believed that galaxy formation was a gradual, slow process. The theory was simple. Clumps of gas and dark matter slowly pulled together under the force of gravity, forming stars over millions of years. These stars would then gather into clusters, and over time the clusters would come together to form galaxies. This process would take billions of years, a slow, steady accumulation of matter. But then, JD's GSZ 13.0 came into the picture. The discovery of this galaxy challenges that slow, steady narrative. Here's the shocking part. JD's GSZ 13.0 formed rapidly within just a few 100 million years of the Big Bang. That's a blink of an eye in the universe's timeline, an incredibly fast rate of galaxy formation by cosmic standards. How did this happen? To understand how this galaxy could form so quickly, we need to look at the environment in which galaxies were born. The universe during this early period was vastly different from today. There was no organized structure yet, no large galaxies, no supermassive black holes pulling matter together. Instead, the universe was full of hydrogen gas, dark matter, and radiation, all interacting in complex ways. The hydrogen gas was mostly neutral, not yet ionized, and it was highly susceptible to the forces acting upon it. This is where dark matter comes in. Dark matter is invisible. It doesn't emit or interact with light, but it has mass, and that mass exerts gravitational pull. The presence of dark matter could have acted as a scaffolding, helping to guide the formation of early galaxies. While we can't see dark matter directly, we know it's out there because of the way galaxies and clusters of galaxies behave. It's the glue that holds everything together. So, how did JD's GSZ 13.0 manage to form so quickly? One possibility is that the presence of dark matter allowed gas to collapse faster than it would have on its own. The gas in these early galaxies could have clumped together more efficiently due to the gravitational pull of dark matter, speeding up the formation of stars. And when stars began to form, They likely were much more massive than the stars we see today. These massive stars burn through their fuel quickly, creating intense radiation that could have triggered the formation of more stars, creating a self-perpetuating cycle. It's also important to consider the role of radiation. The early universe wasn't just dark and quiet, it was bursting with radiation from the very first stars and galaxies. As these stars began to shine, they ionized the surrounding hydrogen gas, transforming the very fabric of the universe. This process, known as reionization, played a crucial role in shaping the early universe, as it allowed light to travel freely through space. Without reionization, the universe would still be a foggy, opaque mess, making it nearly impossible to see distant galaxies like JD's GSZ 13-0. This galaxy is not just a bystander in this process, it's evidence of reionization in action. The light we're seeing from JD's GSZ 13-0 is a result of stars in that galaxy ionizing the gas around them. It's a direct connection to that key moment in cosmic history, when the universe went from being dark and opaque to being transparent, allowing us to see the cosmos as we do today. But there's another possibility. Maybe galaxy formation was driven by more than just gas and dark matter. Could the earliest galaxies have been influenced by massive black holes lurking at their centers? We know that supermassive black holes exist in the hearts of galaxies today, but scientists have long debated when these monstrous objects began to form. The discovery of JD's GSZ 13-0 could offer clues to this. If this galaxy already had a black hole at its center, that black hole could have played a key role in accelerating the formation of stars. The black hole would have generated immense gravitational energy, which could have helped pull gas together to form stars and galaxies at a much faster rate than previously thought. It's also worth noting that the process of galaxy formation isn't just about gathering gas and dust. There's another crucial factor: feedback from stars. When stars form, they don't just sit there and shine. They also release powerful winds and radiation that can blow gas away, limiting how much gas can accumulate to form more stars. This is called feedback, and it's a delicate balancing act. Too much feedback and the galaxy can't form enough stars. Too little, and the galaxy grows out of control. JD's GSZ 13-0, with its rapid formation, suggests that the balance between star formation and feedback may have been different in the early universe. Perhaps galaxies formed faster because the feedback wasn't as disruptive, or maybe the early stars didn't have the same powerful winds as their modern counterparts. The discovery of this galaxy forces us to rethink the way galaxies form in the early universe. The question isn't just how galaxies like JD's GSZ 13-0 came together so quickly, but why? What made this galaxy different? Was it the local conditions, the amount of dark matter, or the presence of early black holes? Or perhaps a combination of all these factors? And there's more. The implications of JD's GSZ 13-0's rapid formation reach far beyond galaxy formation itself. This discovery has ripple effects across our understanding of the entire universe. How did these early galaxies affect the growth of cosmic structures? How did they interact with one another? Were there other, even older galaxies waiting to be discovered? These are the questions that will shape the future of cosmic research for decades to come. But here's the most exciting part. This is just the beginning. JD's GSZ 13-0 is not the only galaxy out there from the early universe. It's likely that there are many more, older, more distant galaxies that remain hidden from our view. Thanks to the incredible power of JWST, we're about to open the doors to an entirely new era of cosmic discovery. And who knows what we'll uncover next. As we venture further into the cosmos, the story of galaxy formation becomes even more thrilling. With JD's GSZ 13-0, we're not just looking at a single galaxy, we're peering into an entirely new chapter of the universe's evolution. The discovery of this galaxy represents a breakthrough in how we study the early universe, and it's opening the doors to a new era of cosmic exploration. Thanks to the unmatched power of the James Webb Space Telescope, we now have the tools to go back in time, deep into the origins of galaxies, stars, and even the very building blocks of everything we know. What makes JWST so revolutionary isn't just the sheer distance it can see, but the way it does so. Unlike its predecessors, such as Hubble, which captured stunning images in visible and ultraviolet light, JWST operates in the infrared spectrum. This gives it the ability to peer through the cosmic fog that often obscures our view of the distant universe, and to uncover galaxies and stars that are otherwise invisible. Infrared light can travel through dust clouds and other cosmic obstructions, revealing the faintest and earliest objects in the universe. JWST GSZ130 is a perfect example of this power. Because this galaxy formed so long ago, its light has traveled through space for over 13 billion years, stretching and shifting due to the expansion of the universe. The longer light travels, the more it gets stretched into longer wavelengths, into the infrared part of the spectrum. Without JWST, this galaxy's light would be completely invisible to us, lost in the vastness of space. But because of this cutting-edge telescope, we're able to see it clearly and study it in unprecedented detail. This is where the magic happens. JWST doesn't just give us a static snapshot of the universe. It allows us to explore it dynamically. The telescope is equipped with advanced instruments, like the Near-Infrared Camera, NIRCam, and the Mid-Infrared Instrument, MIRI, each capable of capturing data in wavelengths that reveal critical information about the distant universe. These tools allow us to not only spot galaxies, but also to measure their size, composition, and even the rate at which stars are forming inside them. With these capabilities, scientists are now able to map out the birth and evolution of galaxies, in real time, taking us from the first moments after the Big Bang to the complex cosmic structures we observe today. JWST GSZ130 is just the tip of the iceberg. This galaxy is a window into a much larger question. How do galaxies evolve over time? What role do black holes, dark matter, and even the surrounding cosmic environment play in this process? These are the questions that JWST will help answer, with each new discovery pushing our understanding of the universe further than ever before. Let's pause for a moment and reflect on what this really means. Before JWST, our understanding of the universe's early years was largely based on theoretical models. We had clues, sure, radiation left over from the Big Bang, the cosmic microwave background, CMB, and the observation of galaxies from later stages in the universe's life. But those were all indirect pieces of the puzzle. JWST is changing that. It's not just observing the universe from afar, it's giving us direct data from the most distant and ancient corners of the cosmos. This is the closest we've ever come to witnessing the universe's birth in real time. One of the most exciting aspects of this discovery is the way it challenges our existing models. For years, scientists have debated how galaxies form. Some have argued that galaxies should grow slowly, with stars and gas gradually accumulating over billions of years. Others have suggested that the universe's first galaxies might have formed rapidly, as we're seeing with JWST GSZ130. What's remarkable about this galaxy is that it appears to have formed faster than anything we expected. The speed at which it grew challenges our understanding of how quickly galaxies can develop. Did it form quickly because of special conditions? Was there an early burst of star formation that accelerated the process? These are the kinds of questions JWST is poised to answer. Even more intriguing is the possibility that this galaxy, like others in its era, could have been part of a larger cosmic structure that we've yet to fully understand. What if these early galaxies weren't isolated islands of stars, but were part of an interconnected network that shaped the universe as a whole? Could the earliest galaxies have been forming in clusters, interacting with one another in ways that have left subtle imprints on their structure? JWST GSZ130 is already hinting at the answer. This galaxy doesn't exist in a vacuum. It's part of a larger cosmic web, a network of galaxies that are slowly coming together through gravity. By studying galaxies like this one, scientists can begin to understand the larger forces at play during the universe's early years, but we're still only scratching the surface. One of the biggest questions remaining is the role of supermassive black holes in the formation of early galaxies. We know that massive black holes exist at the centers of most galaxies today. These black holes are incredibly powerful. They pull in matter, they emit high-energy radiation, and they shape the entire galaxy around them. But when did these black holes form, and how did they influence galaxy growth? JIDE's GSZ13.0 might be able to shed light on these questions as well. If this galaxy already has a supermassive black hole at its center, something that scientists have speculated, it could have played a major role in shaping the galaxy's formation. The black hole's gravity would have acted as a cosmic anchor, pulling gas and dust together to form stars at a rapid pace. In fact, some researchers believe that these early black holes may have seated themselves at the center of galaxies and then helped those galaxies grow by attracting surrounding matter. If JIDE's GSZ13.0's black hole is already in place, it could be evidence of this process in action. The implications of this are huge. If we find that supermassive black holes were common in the early universe, it could force us to rethink the entire history of black hole evolution. Instead of slowly building up over billions of years, these black holes might have been born in the hearts of the universe's first galaxies, kicking off a chain of events that would shape the rest of cosmic history. So where do we go from here? The discovery of JIDE's GSZ13.0 marks just the beginning of a new era in cosmic exploration. With JWST poised to discover more ancient galaxies, we have the opportunity to explore not just one galaxy, but an entire class of galaxies that formed in the universe's early years. Each discovery brings us closer to answering fundamental questions about the nature of the universe itself, questions that have puzzled scientists for centuries. The discovery of JIDE's GSZ13.0 is more than just a milestone in our quest to understand galaxy formation. It's a moment that will echo through the halls of science for decades to come, shaping how we approach the cosmos and the mysteries it holds. This galaxy, and others like it, are not merely artifacts from the past. They are the keys to unlocking the very essence of how the universe evolved. But what does this discovery really mean for the future of astronomy and for our understanding of the universe as a whole? First, let's talk about the implications for future space exploration. With JWST's capabilities, we're entering an entirely new phase of cosmic discovery. The telescope's infrared vision has already shown us galaxies that are older and more distant than anything we've ever seen before. But we're still just beginning to scratch the surface. The James Webb Space Telescope is capable of seeing even farther back in time, to the very edge of the universe, perhaps even to the first galaxies that formed after the Big Bang itself. And these aren't just any galaxies, they're the progenitors of everything that followed. Studying them will give us insights not only into how galaxies formed, but also into the fundamental processes that shaped the universe's earliest days. But it's not just about looking backward. The data we're gathering from galaxies like JIDE's GSZ13.0 will also help us understand how galaxies evolve and interact over time. By observing the light from these ancient galaxies, scientists can trace their paths, their growth, and their eventual merging into the sprawling cosmic structures we see today. As we discover more galaxies from this era, we'll be able to chart the formation of the universe's cosmic web, the vast interconnected network of galaxies, clusters and filaments that stretches across space. This is no longer just a theoretical model. It's something we can observe and study in real time, and it will reshape our understanding of the universe's large-scale structure. We can also expect groundbreaking advancements in our understanding of dark matter and dark energy. These mysterious forces make up most of the universe, yet we still know very little about them. By studying the formation of galaxies in the early universe, we can better understand the role of dark matter in galaxy growth. For instance, the way galaxies like JIDE's GSZ13.0 formed and clustered together could provide vital clues about how dark matter behaves and how it influences the formation of cosmic structures. The discoveries we make today will have lasting effects on everything from the nature of gravity to the fundamental laws of physics. Then there's the question of supermassive black holes. One of the most captivating aspects of the early universe is the role that these titanic objects may have played in galaxy formation. If galaxies like JIDE's GSZ13.0 did indeed form around black holes, This could change our understanding of black hole evolution. Were black holes already in place at the very start of galaxy formation, or did they emerge later as galaxies began to grow? And how did these early black holes interact with the gas and stars in their host galaxies? As we discover more ancient galaxies, these questions will take center stage, pushing us to refine our models of both black holes and galaxy evolution. But there's an even bigger question hanging over all of this. What are we really learning about the nature of time itself? The light we're seeing from JD's GSZ 13.0 has traveled over 13 billion years to reach us. That means we're looking at a time in the universe's history when things were fundamentally different, before the universe was even a billion years old. This galaxy is like a fossil, preserving a moment in time when the universe was still taking shape. In a sense, when we study galaxies like JD's GSZ 13.0, we're not just studying distant stars or ancient gas clouds. We're studying the very fabric of time. Each discovery from this epoch helps us piece together the larger story of the universe's evolution, answering fundamental questions about its past, present, and future. But what does this mean for us personally? As human beings, we've always looked to the stars for meaning. From ancient civilizations, who saw constellations as guides to our fate, to modern-day scientists who search for the origins of life and the universe itself, the cosmos has always held a mirror to our deepest questions. The discovery of galaxies like JD's GSZ 13.0 is not just a scientific achievement. It's a humbling reminder of how much more there is to explore. It's a testament to our relentless curiosity and our drive to understand the world around us. And it's a sign that no matter how much we uncover, there's always more to discover, always more mysteries to solve. As we look ahead, there's one final thought that lingers. What will we find next? The universe is vast, and we've only just begun to scratch the surface. If galaxies like JD's GSZ 13.0 exist, then there are surely many more, even older and more distant, waiting to be uncovered. What other surprises lie hidden in the depths of space? What new discoveries will continue to challenge our understanding of the cosmos and our place within it? For now, we can only marvel at the magnitude of what we've already achieved. The discovery of the earliest galaxy ever spotted is more than just an extraordinary scientific milestone. It's the beginning of a new era in cosmic exploration. As we push further into the unknown, one thing is certain: the universe is far more complex, far more beautiful, and far more mysterious than we could ever have imagined.